Hi, this is Tzvi Rosen. Today we'll be talking about ideals in this second lecture of the Commutative Algebra course. And the theme that's going to be going throughout our lecture is that whenever we have special properties of an ideal in our ring, those will translate into special properties of the quotient ring by that ideal. And we'll start with the prime ideal. So we say we'll have P in A be an ideal. So P is prime if for any elements x and y in the ring, if the product of those two elements is in P, that means that either x is in P or y is in P. Okay, and that's the definition of a prime ideal. Okay, and this comes obviously from the prime numbers among the integers. Whenever you have a product with a prime factor, that had to be found in one of the initial factors. Okay, and going back to our theme that properties of the ideal translate into properties of the quotient ring, the quotient of a ring by a prime ideal is an integral domain. And let's see why that's the case. Recall that an integral domain is a ring without any zero divisors. Okay, well, what does it mean if the quotient by P has no zero divisors? That means, so if A mod P is an integral domain, that means that for any x and y in A mod P, if xy is congruent to 0, or is equal to 0 in the quotient ring, then that means that x is 0 or y is 0. And this is all mod P, because otherwise we would have zero divisors. But what that means is that if xy is in P, that means that x is in P or y is in P. Okay, and this is really an equivalence of conditions, not just an implication. X is in P or y is in P, and that is precisely the definition of P being prime. So what we've established here is the condition of being prime is equivalent to the condition of the quotient being an integral domain. Okay, now let's take a look at some examples of prime ideals and the quotients. So if we have, first of all, we could take any irreducible polynomial. For instance, let's take it to be in a polynomial ring over a field. For instance, we could have x minus I as an ideal, so the ideal generated by x minus I in the ring of polynomials with complex coefficients. Or we could have the ring generated by x squared plus 1 in the ring of polynomials with real coefficients. Obviously, x squared plus 1 reduces, it factors over the complex numbers, but it doesn't factor over the reals, and so this is still a prime ideal there. Great. So another classic example, which I mentioned already, is the integers. So in Z, prime ideals are precisely pz for p prime, p and z prime. Okay, your favorite prime numbers, 2, 3, 5, 7, 11, etc. Okay. So what wouldn't be a prime ideal? Well, for instance, so let's look at non-examples. For instance, x squared in the polynomial ring over the integers, this is not an integral, this is not a prime ideal because x is not in the ideal, but if you multiply x by itself, you get x squared, which is in the ideal. So that means that this is not prime. Equivalently, the quotient by x squared has a zero divisor, which would be x. Okay, any composite integer, for example, 6, this gives us a non-prime ideal. Okay, because after all, 2 times 3 is 6, but neither of those are in the ideal generated by 6. Okay. Prime ideals have some nice properties, particularly the fact that preimages of prime ideals are prime. So if you take, let's let f from A to B be a ring homomorphism. Okay, and let's let P in B be a prime ideal. Then the preimage under f of P as an ideal of A is a prime ideal. Okay, and you can see that simply by examining a product in f inverse of P. So suppose xy is in f inverse of P, excuse me, then because it's in the preimage of P, if I apply the homomorphism f to it, f of xy is in P, but by properties of a homomorphism, f of xy is equal to f of x, f of y. Okay, so that's just by homomorphism. And once we have f of x, f of y in P, well, that implies that f of x or f of y is in P as well, by primeness. And that means that f inverse, or rather, x or y is in f inverse of P, which is precisely what we were trying to prove to show that this is prime. Okay. So the images, on the other hand, if you take a ring homomorphism and apply a see how it acts on a prime ideal inside a ring, that is not in general prime. In fact, it's not in general an ideal. So for instance, if you have the integers and you map them by the identity into the rationals, so here there are all sorts of ideals, so lots of primes. And in Q, because it's a field, it only has 2 ideals altogether. So this is 2 ideals. And only the 0 ideal is prime. But obviously, when you map by the identity, the ideal generated by 2 maps to the set of integers 2z as a subset of q, but that's not an ideal. Okay. So even in cases where an ideal does map to a prime ideal does map to an ideal, it's still not necessarily going to be prime. So an example of this would be if you take let's give it a different name. Let's map this. So we'll map this to x. Okay, so if we map the variable y to the polynomial x squared minus 1, okay, this is a valid ring homomorphism. And the image of the ideal y will be the ideal generated by x squared minus 1. And though this is an ideal, it's not a prime ideal because you have x plus 1 and x minus 1, which multiply into the ideal. Okay, so it's preimages that behave nicely for prime ideals, but images absolutely not. Okay, so now we've discussed prime ideals a good amount, and now we'll discuss maximal ideals. So a maximal ideal is a proper ideal. So that means it's not equal to the whole ring, often denoted by a fracture n in our ring A. Such that there is no other ideal between other ideal I, such that M is properly contained in I is properly contained in A. Okay, so the only ideals between M and A are just M and A themselves. Okay. So that's maximal ideal. Okay, and again, the theme of the lecture, whenever you learn about a new ideal, you look for the quotient ring. So what's the quotient ring going to look like for a maximal ideal? And the quotient ring will be a field. So how do we show that this is the case? Well, we know that A mod M, the ideals of A mod M, let's start this over. And this is by proposition 1.1, which we discussed last time. The ideals of are in bijection with the ideals of A containing M. Okay, we know that latter set is going to just be two ideals. Okay, so two ideals, M and A, but the first ring has to have at least two ideals, so it must have exactly two ideals, namely the 0 ideal and the whole ring A mod M must be only ideals of A mod M. And if those are the only ideals, we've shown already that that means that A mod M must be a field. Okay. And let's look at a few examples of maximal ideals and the corresponding quotient fields. So if we have, for instance, z, so pz are maximal ideals as well as being prime ideals. And z mod pz we know are fields. Okay, obviously this is with p prime. Okay. So if we think about the polynomial ring O with complex coefficients in one variable, all of the maximal ideals look like the ideal generated by x minus a for a some complex number. And this is a consequence of the fundamental theorem of algebra. You can convince yourself of that. So this means that C adjoin x mod x minus a, this is going to be isomorphic to, as a field to C. Okay, and it's just by evaluating, you take any polynomial in x, evaluate it at x equals a, and the resulting complex number is the element of the field. Okay, so this is obviously also a field. Okay, another ring, this time with somewhat more interesting maximal ideals, is if you take real polynomials, polynomials with real coefficients, so the maximal ideals will be of two forms. So you can have x minus a for a real, but you can also have x squared plus ax plus b irreducible. If you take the first kind, then the quotient ideal is going to be isomorphic to the reals. But if you take the latter, this is going to be isomorphic to C. And if you want to convince yourself that that's true, think about what happens when the polynomial is x squared plus 1, and then you're looking at polynomials with real coefficients with degree at most 1. So it will be numbers of the form a plus bx. That looks basically like complex numbers. Okay, so now we've seen some prime ideals, we've seen some maximal ideals, and now I'll prove to you that maximal ideals are prime. And this is relatively trivial because we know that an ideal P is prime if and only if A mod P is an integral domain, but if M is maximal, that means that A mod M is a field, and a field is an integral domain. So that means that M itself must be, M itself must be an integral, prime ideal. Okay. So a result that's proved in Natia MacDonald, which is true in vast generality, is that every ring has a maximal ideal. And since we're putting very few conditions here, we're just saying it's any commutative ring, we have to use some fancy techniques, in particular Zorn's lemma. And the way that we're going to apply Zorn's lemma is as follows. So we're going to say, if we let's use Zorn's lemma in this form. If we let sigma be a family, in particular non-empty family, such that every chain, okay, and that's a chain is a totally ordered set, every chain in sigma has an upper bound, then sigma has a maximal element. Okay, so we just have to prove that these conditions are satisfied for the ideals of a ring, and then we'll be able to find a maximal element. And in particular, it has to be the proper ideals of a ring. So obviously, sigma is the set of proper ideals of A. Okay, this has to be a non-empty family, and it is non-empty because we have the zero ideal. And just to verify that 0 is in fact a proper ideal, we should specify that this is not equal to the zero ring. Okay? So next we just need to show that every chain is bounded. So suppose we have a chain of ideals ordered by inclusion. And we've got A1 contained in A2, etc. So we need to show that this is upper bounded. So we claim that the ideal A, defined as the union over all I in the index set of AI, is an upper bound. Okay, so it's an upper bound, and it has to be a proper ideal, otherwise it wouldn't be an upper bound within the family, within sigma. An upper bound in sigma. Okay, and well, the fact that it's an upper bound is relatively straightforward because it's a union. Every ideal every element you can find in this in any ideal in this chain will be in the union. So that's an upper bound on all of the ideals. But whether it's actually in sigma, we have to show that this is a proper ideal. So it's not equal to the whole ring. Well, if A, suppose A were equal to the whole ring, well, that would mean that 1 was in A. But A is a union, and so that would mean that there is some I such that 1 would be in AI. Because if you're in a union, then you must be in one of the constituent pieces. But that would be a contradiction because we know that AI is supposed to be proper. So this is a contradiction since AI is proper. So that means that A is an upper bound in sigma. And then Sorden's lemma implies that there's a maximal element of sigma. Okay, so that's how we get our maximal ideal. And there are lots of rings where it's much easier than this to prove that there's a maximal ideal, but this is the greatest generality we could do. Okay, so we showed earlier that maximal ideals are prime. In general, prime ideals do not have to be maximal, but for a principal ideal domain, they are. So let's recall that a principal ideal domain, or a PID, is an integral domain in which every ideal is principal. We'll claim that every non-zero prime ideal in a PID is maximal. So let's show this to be the case. So let X be an ideal not equal to the zero ideal. And let's suppose we have, sorry. Let's start with P prime. Okay. So we'll start with prime and we'll deduce maximal. So we have P, because it's a PID, P can be written as X. Okay. Oh, and we're saying this is non-zero as well. Okay. This can be written as X since it's principal ideal domain, and this is not equal to 0. Okay, so suppose X is contained in some other ideal. And so, again, we're in a PID, so this can be written as being generated by Y. That means that since Y generates X, that means that there's going to be some element Z in our ring, let's call it A, such that X is equal to YZ. Okay, so far so good. But we know that X is a prime ideal, right, by hypothesis. So since YZ is now an X, that means that Y is an X, or Z is an X. Okay, so if Y is an X, then we're just talking about the ideal itself, so this can't be the case. So that must mean that Z must be an X, in which case Z can be written as Tx for some T. But if Z is Tx, we had X equals YZ, that means that X is equal to YTx. But in an integral domain, you can cancel, and that tells us that YT must be equal to the multiplicative identity. And if YT is equal to the multiplicative identity, that means that the ideal Y must be the whole ring, which implies that X was maximal. Okay, so in a PID, all primes are maximal. Okay, having looked at primes and maximal ideals, we're going to define another couple special ideals in a ring. We'll start with a nilradical. So the nilradical N is a set of nilpotent elements of the ring A. Okay, and we're going to claim that the nilradical, this set of nilpotent elements, is in fact an ideal. And so that means that we need to show that the set of nilpotent elements is closed under scaling by A and is closed under addition. So first, so suppose X is in N. That means that there exists a K such that X to the K equals 0. But if then if you take any A in the ring, AX to the K is A to the K X to the K, since our rings are all commutative. And that's going to be equal to 0, because X to the K, as we've already said, is 0. Okay, closure under addition is a bit trickier. So if we have X and Y in the nilradical, we're going to have two integers, m and n, such that x to the m is 0 and y to the n is 0. Well, if that's the case, let's consider what happens when we raise x plus y to the m plus n minus 1 power. This is going to be the sum from k equals 0 to m plus n minus 1 of ak x to the k y to the m plus n minus 1 minus k. Okay, and ak is just going to be, depending on the ring, some integer or something like an integer. This is just coefficients, possibly in z. And then x to the k, so from k equals, so for any k greater than m, x to the k, greater than or equal to m, x to the k will be 0 by the fact that x to the m is 0. As for y to the m plus n minus 1 minus k, if k is smaller than m, that means that we're looking at, so for instance, if it's m minus 1 or less, then this is going to have a power greater than n, which means that it'll have a factor of y to the n, which is 0, so all of these terms are going to vanish. So that'll be 0, which means that x plus y itself is in the nil radical, which means that it's closed under addition. So our claim is verified. Okay. And recalling our theme, whenever we have a new ideal with special properties, we want to think about the quotient. The quotient is a reduced ring. And what it means to be reduced is as follows. A ring is reduced if it has no nilpotent elements. Okay, so when you quotient by the nil radical, you get rid of all of the nilpotents in your ring. This actually, we should justify this, so let's prove this claim that the quotient by the nil radical, it has no nilpotents. So suppose we have x in A mod n such that x to the n equals 0. Okay? Well, when we have this kind of relationship in quotient rings, what that means is that in the original ring, there exists some representative x tilde such that x tilde to the n is in n. But what does it mean for some element to be in n? It means that it's nilpotent. So there must exist some k such that x tilde to the n, x tilde to the n raised to the kth power equals 0. But that means that x tilde itself raised to the nk power is 0, and that means that x tilde is in n, which means that x is 0 in A mod n. I should adjust this a bit. If it has no nilpotent elements besides 0. Okay, so if any nilpotent element is 0, that means that the ring is reduced, and that's the case for the quotient by the nil radical. Okay, here's a theorem from Atiyah MacDonald that the nil radical, which again we've just defined in terms of nilpotent elements, it's actually the intersection of all prime ideals in the ring. And let's prove this. So suppose let's name this n prime. So first we can show that n is in n prime. So let's take any nilpotent element. So for any x in n, x to the n equals 0, but we know that 0 is in any prime ideal. So 0 is in P for all P prime. But if we want this ideal to remain prime, we need to make sure that these things multiplying to 0 also show up in the ideal. So that means that x will also be in P, okay, for all P prime. And that means that x will be in n prime, the intersection of all prime ideals. Going the other way, if we have n, we want to show that n prime is contained in n. So to show that n prime is contained in n, we're going to prove the contrapositive. So to show that if something's not in n, then it can't be in n prime. So we're going to take f such that f to the n is not equal to 0 for all n. Okay, so this is a non-nilpotent element. Okay, now we're going to make a similar Zorn's lemma argument to the one we did before. So let's set up a family of ideals sigma, but instead of being all the ideals in the ring, this is going to be all the ideals containing no power of f. No powers of f. Okay, and we know that this is non-empty because the 0 ideal is in the family sigma because, as we said, f is not nilpotent, so no power is equal to 0. Similarly, the boundedness of chains comes just as above. So chains are bounded by the reasoning of before, just taking the union of the ideals in the chain, above as before. And so by Zorn, sigma has a maximal element. Okay. So we're going to claim that that maximal element that we just found using Zorn's lemma is actually a prime ideal. So, oops. So if we let P be the maximal element of sigma, we're going to claim that P is prime. Okay, and the way we're going to show that, we'll use the kind of contrapositive version of the primeness condition. So we know that in general, primeness is given by, if we have x, y, and p, then that means that x is in P or y is in P. So we're just going to flip that around. So if x is not in P and y is not in P, then that will imply xy is not in P. Okay, and these two statements are equivalent since they're basically contrapositives. And we're going to use the latter to prove that this P is prime. So we'll start with the assumption that x and y are not in P, that means that p plus x and p plus y as ideals are not equal to p. Okay, and since p is maximal in sigma, that means that they're not in sigma. Okay, and since they're not in sigma, that means that there's some power of f in both of them. So we can take m and n such that f to the m is in p plus x, and f to the n is in p plus y. Okay? Well, now that we have f to the m in p plus x and f to the n in p plus y, just multiplying those together, we get f to the m plus n must be in p plus xy. And since when we distribute p plus x times p plus y, the p absorbs x and y, and you're just left with p plus xy here. But what this implies is that p plus xy is not in sigma, which means that xy is not in p. And that's exactly what we needed to prove to show that p is prime. And this tells us that that we have a prime ideal that does not contain this element. So for any non-nilpotent element, there's going to be a prime ideal that doesn't contain it. And so that means that the intersection of all primes is contained in the set of nilpotent elements. Okay. Okay, so that was the nil radical, and now we'll discuss the Jacobson radical. So this is defined rather simply as the intersection of all maximal ideals in A is the Jacobson radical. Okay, so just as we saw that the nil radical is the intersection of all prime ideals, Jacobson radical is the intersection of all maximal ideals. An alternative definition is that something is in the Jacobson radical, element x is in the Jacobson radical, if and only if 1 minus xy is a unit in A for all y in A. So we're going to prove this by contradiction by supposing first that x is in R. Suppose x is in the Jacobson radical, but 1 minus xy is not a unit. Okay, so whenever you have something that's not a unit, it must be contained in some maximal ideal. And you can use our Zorn's lemma argument to verify that. So this is in some maximal ideal M. But we know that x is in the Jacobson radical, so it's in every maximal ideal. So we know that x is also in M. But because this is an ideal, that means that xy is in M, which means that 1 minus xy plus xy is in M. But that's just 1. Okay, and obviously you can't have 1 in a maximal ideal, otherwise it would be the whole ring. So that's a contradiction. Okay. Let's move the other way. So that tells us that 1 minus xy has to be a unit. Let's go the other way. So now we're going to suppose that x is not in the Jacobson radical. So we're proving the contrapositive. Okay, so if you're not in the Jacobson radical, that means that there's some maximal ideal that you're excluded from. So there's a maximal ideal M such that x is not in M. Okay. But if you're not in a maximal ideal, then if I try to add you in, that must mean you pick up the whole ring. So this implies that m plus x is the whole ring, which implies that I can write 1 in terms of u, I can write 1 in terms of u and x, so where u is in the maximal ideal. Okay, and y is some element of the ring. But then this means that u, an element of the maximal ideal, is going to be equal to 1 minus xy, which, and we've already specified that u is in the maximal ideal, so that means that 1 minus xy is not a unit for this choice of y, which tells us that if x is not in R, then 1 minus xy is not a unit for every y, and that proves the converse direction. Okay, as for whether n is contained in R, this is relatively straightforward. We know that n is intersection over prime ideals. And R, this is the intersection of all maximal ideals. The set of maximal ideals, so this set, is contained in this set, in the set of primes. Maximals are primes, but there are more primes besides that. But if you have an intersection which is being carried out on a larger set of sets, that means the intersection is going to get smaller. So that means that n is going to be contained in R. Another way to think about this is if you have, well, we know that n is defined as the nilpotent elements, whereas R is defined as the elements that have this 1 minus xy being a unit property. Well, let's consider what happens if we take x nilpotent. Can we see if it satisfies this 1 minus xy property? So 1 minus xy needs to be a unit for all y. Well, I can actually, if x to the n, if x is nilpotent, that means x to the n is 0. And then I can just multiply this by 1 plus xy squared all the way up to xy to the n minus 1. And then the result of that multiplication is going to be 1 minus xy to the n. And since x to the n is 0, this will be 1. So any nilpotent element trivially satisfies this requirement of elements of the Jacobson radical. And that's another way to verify this containment. As for the quotient of A by, this should be R. So we saw that the quotient by the nil radical is going to be a reduced ring. The quotient by the Jacobson radical is going to be a special type of ring called a semi-primitive ring. And the definition of semi-primitivity has to do with the fact that the only element annihilating all simple R modules, where R is the quotient ring, is 0. Okay, so that's semi-primitivity. I don't expect you to understand this definition, but it's useful. And the other place that R comes up, the Jacobson radical, is in our discussion of the Nullstellensatz. So when we get to the Nullstellensatz, the Jacobson radical is going to be of great importance. All right, thank you so much for your attention, and I'll see you next lecture.